Okay, so we're talking about spherical coordinates. And so we said that cylindrical coordinates was slightly familiar because it's so similar to a type A polar triple integral, right? Type A meaning if we go bottom surface to top surface, which is the z coordinate, right? Z is a function of x and y, and z is a function of x and y. We go bottom to top, and then we project into the xy plane and do a polar double integral. That's basically what cylindrical coordinates is, right? R theta z. And so we saw it's called cylindrical coordinates because how would you define a cylinder? It's not going to work. What did we do? We said square root of. So R is what? Square root of x squared plus y squared, because it's the hypotenuse, right, of the x and y coordinate, the hypotenuse of that triangle. So if we said that equals, say, 2, so that's R equals 2, right? R equals 2 gives you a cylinder, right? It gives you a cylinder. So cylindrical coordinates are based on really easily defining cylinders. R equals 2, R equals 1 defines the cylinder. A circular cylinder, right? A circular cylinder. Okay, so now we're doing now we got to spherical coordinates, and you had practice in the web work, and I trust that went pretty well because it wasn't a big stretch from what we'd already done with triple integrals. All right, so just you're working in z and polar coordinates, right? But now we said spherical coordinates is a whole different beast, okay? We said, first of all, rho. So we have 3 coordinates. First, rho is the distance from your point, whatever point you have, it's the distance to the origin in R3. So that's truly the distance, no matter where your point is, it's the distance away. So it's like the length of that blue line. And then we have the same angle theta, which is what? The angle swept here, counterclockwise from positive x. So that's the same angle we've always talked about. The same trig angle, right? So you have a distance from the origin, and you have an angle, the angle swept counterclockwise from positive x, and then the last coordinate is another angle, right? And that's once you've picked that direction theta, kind of from the z-axis, then phi is the angle then swept down from positive z. So what is it? Yeah. So what are our ranges on these? So rho can be 0 to any positive real number. So rho equals 0 is the origin, and then for you have any positive rho. And then what about theta? Theta is going to go from 0 to 2 pi, and phi is going to go from what to what? 0 to pi, right? 0 would be the positive z-axis. Angle of pi over 2 is when, no matter what direction you're in, you're going to be in the xy plane or the horizontal plane, and then we end at pi, which is half of a rotation takes you down to the negative z-axis. So that defines any point in space, right? With a distance from the origin, a theta this way, and a phi tipped down from z-axis. So we were figuring out the relationships between all those coordinates. So I'm going to do that a little different than we did last time. So here I am at a particular rho, theta, and phi. So what would you just, I guess I'm showing you, but if you hadn't seen it, what would you just predict for theta? Theta is about what here? Pi over 4. It's right, like it's splitting that first octant right in half. Okay, what about phi? What would you guess for phi? Also about pi over 4. It's splitting the difference between the z-axis and the horizontal plane, right? So something like that. Rho, you can't really guess because you don't know what the scale is, right? You have no idea what the scale is. Okay, but let me just tip phi up a little bit higher. So let's make phi more like pi over 6. Okay, that's fine. All right, so we were drawing all these coordinates and finding our relationships between coordinates. And that's going to be really important when it comes to if I do this, I'm always going to end up in the middle. Yeah, that's not going to work. Okay. So let's draw it here. So first of all, if I wanted to show the z coordinate of this point, right? So you could write this point as x, y, and z. We could write this point as r theta z, and we could write this point as rho theta phi. So what about, so let's talk about z first. What is z? No, the meaning of z for this point. Yes, it's distance up from the xy plane, right? Something like this. That's z. Okay? And then we butchered x and y last time, and if you noticed that and didn't say anything, shame on you. What is the x coordinate of the point? If you didn't notice, then that's okay. But if you did notice and you didn't speak up, then that's the problem that I have. Okay. What is x? What is x coordinate of this point? Yeah, distance from the YZ plane. How far we go forward or back, right? In or out of the page. Okay? So in this case, is x positive or negative? Positive, okay? And it's this here. I think I labeled this as y last time. Okay, and then what is y? So now y is how far to the right or left we go, right? In this rendering, it's how far to the left or right. So that's how we would define x, y, and z for this point. And that's old hat, right? So that's just our rectangular coordinates for R3. So then what is R? Okay, R squared is x squared plus y squared. So how would you describe R as we would label it in this picture? Yep, so R would be the distance in the xy plane to this projection point right here, right? So this would be R here. Distance from the z-axis, right? So that's the distance from the z-axis to the point is R. And what about theta? Theta is the same angle. Swept counterclockwise from the positive x-axis. There's theta. So that's like a horizontal sweeping, right? Horizontal sweeping, parallel to the xy plane. Okay, what's left? Rho is what? Okay, yep. Is it angle? No, distance, right? It's a distance from origin to the point. So I'll make it blue because the line is blue. And finally, what is phi? Phi is that swept down from the z-axis in the direction of theta. So it can be in any direction, right? Theta could this way, or phi this way. So we pick the direction theta like this, and then phi is swept down in that direction of theta. So that's a vertical angle, right? Theta is, think of it as like a horizontal sweeping. Phi is a vertical sweeping down from the z-axis. Okay, so looking at this, so we're working on a triangle up here. So I had put R up here like this, and we were working on this, but I'm going to work, so the same triangle, congruent triangle is here, rho, z, and R, so let's work on this one instead. So what is this angle right here in that triangle? For R, z, and rho, what's that angle right there? That theta? In this vertical triangle. That's a 90. Do you see it? Yeah, R is in the xy plane, z is straight up. That's a 90-degree angle. Okay? What is this angle up here? That's phi. That's phi. Right? It's those are what alternate interior angles. So this is parallel to the z-axis, right? These two are parallel. So this is also phi. And that other angle down there by the origin would be pi over 2 minus phi. Okay. All right, so let's write out what R and Z are here. So R is, so R, look, is the opposite leg from phi. So R is rho sine, right? Sine is opposite. Okay, and we also know that R is, what's another way to define R? Square root of x squared plus y squared. Okay, what is Z? So Z is the leg, right? It's the leg of this, adjacent to phi, therefore, rho cosine phi, adjacent side, right? And so we want to get x and y in spherical coordinates. That means x and y as a function of rho, theta, and phi. Rho, theta, and phi. So if we come down here to this triangle down here, now we know in spherical coordinates what is R? Rho sine phi. So our hypotenuse, so we have this triangle that's x, y are the legs, and the hypotenuse is rho sine phi. So see if you can write down what x and y are in. So this right here is rho sine phi. See if you can write down x and y in spherical coordinates. What would x and y be in terms of phi, theta, and rho? See if you can do it. If R is rho sine phi, and you're looking at this right triangle down here. Everyone think to themselves, see if you can do it. So hint, x is what? What is it? The adjacent side of theta. If it's the adjacent side of theta, then rho sine phi, which is R, times cosine theta. So we knew before that x was r cosine theta, right? That's from polar and from cylindrical coordinates. X equals r cosine theta. But then in cylindrical coordinates, or spherical coordinates, excuse me, r is rho sine phi. So then therefore x is rho sine phi cosine theta. And similarly, y is? It's easy now. Sine theta. So we've got our x, y, z. So theta we can write, we know is arctan of y over x. There's no relationship between theta and phi. Those are two totally independent variables, right? Theta and phi, there's no dependence. There's no relationship between those. Those are chosen independently because they're in different planes, right? Theta, horizontal sweeping angle. Phi, a vertically sweeping angle. So similarly, no relationship between z and theta, right? Those are totally independent quantities. But we have all this relation. X, theta, y, and r are all related. Z, phi, and rho and r are all related. And these are all those relationships. Okay? So now let's talk about what is rho. Let's talk about some different ways to express rho. How could you express rho? So you could do, yeah. So I'll just do rho squared. So rho squared is r squared plus z squared. But then that would also be equal to x squared plus y squared is equal to r squared plus z squared. Again, so why is this called spherical coordinates? Cylindrical coordinates, because it's really easy to define a circular cylinder. Spherical coordinates because how do you define a sphere? Just rho equals a number, right? All points the same distance away from the origin will be a sphere. So by saying rho equals 3, boom, sphere, right? What else am I missing? I think that's everything. Phi? Let's see, what is phi? Yeah, we could write some different things here. So if we were doing it, say in r and rho, so what would phi be in r and rho? Arc sine of r over rho. I don't think I've ever used that before. But yes, that's true. And then that being the case, it's also the arc sine of, we did it in terms of x, y, and z, it'd be arc sine of square root of x squared plus y squared over square root of all three of them added together. Maybe I have used that. That's vaguely familiar. And then the radical x squared plus y squared cancels out, so you get 1 over radical z squared, right? No. Don't do that, right? Sums and differences under radicals are locked. You can't do anything with those. Leave it like this. Don't do things like that, although many calculus students have tried. You can't cancel out things that are added and subtracted in fractions, right? Factors, if you have factors in denominators and numerators, those can reduce. But things that are added and subtracted don't go away in fractions, especially if they're under a radical. All right. Any questions? So now we need to figure out what is a little bit of volume in spherical coordinates. Or in other words, what's our dV? So let's see if I can draw this here. So at this point, we have a change in theta, like this. We have a change in phi, like this. And then we have a change in rho, like this. Not bad. So change in distance from the origin, change in angle phi. So this here is what? A little change in rho. This would be what? This would be our change in, well, it's, so that distance is not the change in theta, but it's going to be based on the change in theta, right? And then this one here is going to be based on, it's not a distance. We need to figure out what these distances are, because our dv is still going to be like base times width times height times length times width times height, length times width times height. But we know that a change in angle measure is not a distance, right? So this is going to be a little based on a little change in phi. Right, this is a little tipping, right? This is a little bit a horizontal swept angle, and then a little change away from the origin, right? So we're going to get this little three-dimensional solid that's going to be like our dv in spherical coordinates. So delta rho is fine. That's a distance. We're good. So what is the distance associated with a change in angle theta? Right? A change in the angle theta results in what distance? What little change in distance? No, it's not y, right? So think about just down here in the xy plane, a little sliver of a change in angle is a little change in arc length. So then how do we, so if we think of this right here as d theta, right? And what is that distance right there? That's the same as this distance right here. Remember how we calculate that? Nope. Just arc length formula, right? Arc length of a circle is what? It's the same thing we did for r, and it's delta theta, right? So yeah, it has to do with how much angle you swept, but then it also is proportional to how far away you are, right? The further you are away, the bigger that change is. So it's r times delta theta. So this distance then is delta theta times r. And so then in spherical coordinates, what is that? Rho sine phi delta theta. All right, and then what's our little distance for a change in phi, right? The change in phi is not a distance, that's a change in angle. So it's also going to be multiplied by what? Rho times the change in phi, right? So imagine, so it's going to be how far out you are, how far out you are away from the origin, times the amount of change in angle. That's going to give your vertical arc length, right? Your vertical arc length. So now we have it. So what will dv be? dv will be length times width times height, made very small, right? So we're going to have d rho, d phi, d theta. But what else do we have? Let me multiply those three together. Right, we're also going to have are you tracking with me, or did I lose you? It's going to be rho squared sine phi. What is that like? The rho squared sine phi is like the r when we did cylindrical coordinates or polar coordinates, we had to do r times dr d theta, because changes in angles don't quite give you change in length, right? It depends on how far you are away from your pole or your origin. So this rho squared sine phi then compensates for how far that thing is away from the origin. So when we do spherical coordinates, our little dv is going to be this, and this rho, just like before, the rho squared sine phi is then going to latch on to the function and become part of what you integrate. So it comes with the dv, but then it multiplies in with your function, and then that's part of the thing that you find the antiderivative of. And so that's similar to the r that we had when we had dr d theta. Okay. So there ended up a lot of writing on there. Does everything make sense? Anybody have a question? So we need this for triple integrals. And in terms of changing those triple integrals between coordinate systems, we need all these relationships. All these over here and all these over here. So given rectangular coordinates, can you switch it into spherical? Given spherical, can you switch it into cylindrical? Given rectangular, can you switch it into cylindrical? Okay, as you've seen examples like that already. But we've got all these relationships over here, and then these over here. Ready for an example? Any questions? Can I erase what's on the screen? Okay, here we go. So we want this one here. We're going to set up the spherical coordinates, the integral of x squared plus y squared plus z squared. That's the function we want to integrate. So we could think of that maybe as a rate of change function, right? That's like a rate of change function. Over the solid defined as this. Inside x squared plus y squared equals 4. Below z equals 5. And outside x squared plus y squared plus z squared equals 4. So we're going to sketch that first. That's, I think, more on the easy side for things to sketch. I think you can do it. So this would definitely be fair game for, you should be able to do this. It's not super hard. So let's sketch that solid first, and then we're going to set up this integral in spherical coordinates. So go, sketch. No, you don't. We're not going to do this. So with spherical, you don't split it up as you do rho. You do them all three separate. You do the rho, and then you do the phi, and you do the theta. Yeah. So yeah, that's a good question. So with the spherical triple integrals, we kind of we don't think of them as the inside integral and then the outside double integral anymore. We just do each variable separately. We're going to think what does rho do? What does phi do? What does theta do? Because there's really no projection, there's no phi theta plane, right? There's no, we can't really get a projection into the phi theta plane thinking in R3. That's too kind of abstract. Okay, so how did the sketch go? I thought that was in here. We'll see. Okay, so x squared plus y squared equals 4. So rather than me doing it, so since you guys have to sketch them, I'll just sketch it. So maybe that's more helpful. So if we can kind of imagine it, if we can kind of imagine a little bit first, then we'll we won't draw a bunch of stuff that we don't need to draw, right? So can you imagine what this will be? If it's inside that cylinder, below z equals 5. So now I've got only this stuff here, right? So here's z equals 5. I've got all this stuff down to negative infinity. And then if it's outside of the sphere, then the sphere kind of acts as what? The bottom, right? So then it's like the top of the sphere will be the bottom of this thing. Okay, so then there'll be the sphere. Okay, so that's like the top of the sphere will act as the bottom, right? And then we'll have and then the top of it will be z equals 5. So something like that. That's a little better. Okay, yeah, so the bottom of it is the top of the sphere, which fits perfectly into the cylinder, and then the lateral sides of the cylinder, and then the top is z equals 5. Okay, so now we're going to go, we're going to have x squared plus y squared plus z squared. And then we're going to have rho squared times rho squared sine phi d rho d phi d theta. We'll have to, yes. Yeah, we're going to have to because our variables are rho, phi, and theta. They're not x, y, and z, right? So what will it apply to? Rho? Rho squared. So this, yes, this becomes rho squared. So then what do we integrate? Rho to the 4th sine phi is what we integrate. So then the rho squared sine phi latches on to the function, and that's what we do the antiderivative of. We good on that? Okay, so now we're going to do rho first. So now for rho, the archer, our arrow man, is at the origin, and he's shooting from the origin out, and so into the solid. And so we say, where does that angle first, how far from the origin, rho, does it first pierce the solid? And then how far from the origin does it leave the solid? Okay, so first of all, the lower limit of integration is how far from the origin, rho, right, does that angle pierce into the solid? What would that be? I'm remembering 2 and 4. 2. Radius is 2. Okay? And then, how far from the origin does the arrow leave? Does it take before the arrow pierces out of the solid?
There's going to be 2.
Okay?
Because you got the wall and then you've got the ceiling.
It depends on what?
Angle.
Which angle?
Phi.
Phi. Depending on phi, we have a different surface that the arrow leaves through. Right? If phi is a low value, then it leaves through what? But not 5. What is 5 equal to? Z, right? So z equals 5. For low values of phi, it leaves out through z equals 5, which we're going to have to get into. So what is z in spherical coordinates? Rho cosine phi. Therefore, the rho value that it leaves that top surface out of for low values of phi is what? Rho equals 5 over cosine phi. Do you see it? Doesn't make sense. For z equals 5, that means rho cosine phi equals 5. We need to know the rho value that it leaves the solid, so the rho value is to solve for rho. 5 over cosine phi, or 5 secant phi if you want. Makes it a little easier to write. But that's only for certain phi. Which phi is that true for? Starting from phi equals 0, the z-axis, until pi over 2 is down here. So we need to figure out what angle phi that is to the edge of where this disk intersects the circular cylinder. You see that? Okay, so our horizontal up there is 2, our vertical is 5. Good. So this is 2, and this is 5. So that phi is arctangent of 2 over 5. So when phi goes from 0 to arctan, can I write a tan? A tan of 2/5. What does rho do? Rho goes from the sphere to, we found it before, 5 secant phi, right? All right, did I lose you? So we found that z value of 5 is the same as rho being 5 secant phi. So enters through, the arrow enters through the sphere at 2 and leaves the top plane at rho equals 5 secant phi. But that's only when the angle phi is between 0 and this angle here, arctangent 2/5. I can't explain it any better than that. Doesn't make sense. Question, please. That's a distance. Because it's not, right? It's only that at that final angle. It's longer here and here and here. For the lower values of phi, it's a longer rho. It's only that rho that you said at the very final angle. Yep. No, shorter. Shorter. That's the longest, right? That's the longest, and then all these other rows are shorter than that, depending on what phi is. No, the 2 is the 2 of the radius of the sphere down here. You see? Yeah, the 2. This 2 is where we enter the solid. Here, this 2 down here. And then where it comes out is then the rho, however far rho is to this horizontal face up here, which is the z equals 5, which is the same as rho equals 5 secant phi. It depends on phi, right? That distance to z equals 5 depends on phi, according to 5 secant phi. And then what's theta here? Theta goes from? Ooh, that was easy, right? Just all the way around, right? Then theta just goes all the way around. But that's only the part, that's like the cone part, right? That's only the part from the sphere like within that cone. So now we need to do plus. Same thing, rho to the 4th sine phi, d rho, d phi, d theta. Okay, and now for values of phi, what, greater, so we're going to start at arctan of 2/5 up until what angle now? Down all the way down to pi over 2, right? So now we're shooting the arrow and it's coming out. Where does it come out now? The wall, the cylinder, right? The vertical wall of the cylinder. So it still pierces into the solid at 2, rho equals 2. But it's going to come out of the solid at this vertical wall, which is y equals 2, that's right. And that's going to be between angles of phi of arctan 2 over 5 and all the way down to the pi over 2, the horizontal plane, right? And then again from 0 to 2 pi. So all we have left is, in terms of rho, what is y equals 2? What's y equals 2 in terms of rho? So what is y? Y equals? Rho sine phi sine theta. And rho is 2, or y is 2, sorry. So 2 equals rho sine phi sine theta. So rho equals 2 cosecant phi cosecant theta. So that depends on, it shouldn't depend on, why does it depend on theta? It shouldn't depend on theta. What are we doing wrong? Ah, right. This is z. This is z equals 2. No, wait a second. This is r equals 2. R equals 2. R equals 2. That's why. Yeah, that shouldn't depend on theta. That shouldn't depend. So r equals 2 means that 2 equals the cosine phi? Rho cosine phi?
It's just sine.
Phi is here.
It's just rho sine phi.
But r is the adjacent angle to phi.
No, it's not from what you explained to us earlier.
Isn't that phi? This is, what the heck?
Phi is.
It's not this distance, right? It's this distance. It's sine, right? Sorry. By putting it here, I keep thinking it's this height here. That's not right. It's r equals 2 is
The distance between.
from the sphere, right? It's
From the
this.
sphere out from the origin.
This is r equals 2 here.
And then if you like angle it up a little bit more, that's.
So it's sine. Sorry. I should not be putting it here. That's what's confusing. Yeah, so r is the distance this way. So then its rho is 2 over sine phi. Good thing you guys are here. I didn't have to do that. All I had to do was enter it. So. Okay. So it's not y. I was thinking it's y. It's r equals rho sine phi. And this cylinder is r equals 2. That's what we're talking about. And so then 2 is rho sine phi, rho is 2. So we got it. So when the angle phi is from 0 to arctan 2/5, the rho is going to be the rho leaving the solid is that z equals 5. And so that's the same as rho equals 5 secant phi. So when that angle phi is between 0 and this red line right here, that distance rho up to here is 5 secant phi. So we go from 2 to 5 secant phi. And then when the angle is from arctan 2 over 5 all the way down to pi over 2, rho goes from 2, the sphere, to r equals 2, which is rho equals 2 cosine phi. Questions on this very good example? It's got everything. Now, if you had the choice, which type of coordinates would you choose to use if you want to do this triple integral? Cylindrical. One easy triple integral, right? So, and that's your written homework for Tuesday has that. Like your number 1, A and B. One of them is a lot more convenient for cylindrical. One of them is a lot more convenient for spherical. But you're going to do both ways because it's a really good learning exercise, okay? But you'll see immediately, if I had the choice, oh, I would definitely do spherical for this one. Or if I had the choice, I'd definitely do cylindrical for this one. But doing it the other way, you get to learn a lot. All right, so questions on this very good example. Yes, please.
Explain the upper bound of rho again.
The upper bound of rho.
For
The second one.
Yeah.
So it's so you see that it's angles of phi greater than this angle,
Yeah.
swept down to pi over 2. You're gonna leave the cylinder, right? So you're gonna enter the sphere is gonna enter the arrow is gonna enter the solid through the sphere, and that's the 2, and it's gonna leave the solid through the cylinder, and that cylinder is defined as r equals 2. Right? If it's the cylinder x squared plus y squared equals 4, that's just r equals 2. And that's where the arrow is going to leave the solid for that range of angles. And so then we used our relationship that r is rho sine phi to get it in terms of rho. So then r is just 2 rho sine phi, solve for rho, 2 over sine phi. Better? Hector?
I probably just missed this, but rho squared,
Uh-huh.
why is that just rho? Because rho equals x squared plus y squared equals
The square root. Did I write that down wrong on a previous screen?
I probably just
Rho is the square root
Oh, okay.
of x squared, right? Because this is just a spherical, this is just the equation of a sphere. Radius squared equals x squared plus y squared plus z squared.
Okay, I just forgot to write the square root.
Yeah, if you just want rho, you need square root. Other questions? Okay, so that concludes triple integrals, and you'll have lots of these to set up in WebWork for Tuesday. But if you like geometry, we're having a ball, right? This is cool stuff, right? Can I erase what's on the screen? Okay, so now we're going to talk about, we're going to change subjects here. And again, everything that we're doing, we're building up to vector calculus. All this stuff, about 80% of what we've done so far is all going to come into play in the end when we're talking about vector calculus and the fundamental theorems of calculus. Yeah, it's awesome. So hope that you're, so just let me emphasize that everything, you can't just like compartmentalize this and say, okay, I got through that homework. It's all going to come back. We're going to see double integrals. We're going to see triple integrals. We're going to see, of course, everything happening here in our R3 that we've been learning, the geometry of things. Okay, so where are we? Okay, so I want to talk about vector fields. So this goes back to our functions, right? So All right, so I want you to have a discussion. The person next to you, what do we mean by each of these things? What kind of function is that? So that a single variable real valued function, what is that? Where have you seen examples of that in your past? A multivariable real valued function, what is that? How does it graph? Where do you see that, and have you seen that in your past? And the past might include this course, right? Single variable vector valued function, what is that? How does it graph? Where have we seen those before? All right, and then a multivariable vector valued function, what might that be? Okay, go. Take 2 minutes. We got to know what these things are. Go.
It's just got one variable.
Second one, that's like
Okay, so how would you characterize a single variable real valued function? Y equals f of x. This is 95% of your math history, right? Y equals f of x. Single variable refers to? What does that refer to? Single variable. Independence. One independent variable. Single variable. One independent variable, which is? X. Real value is referring to what? What is it referring to in y equals f of x, the real value? Y. The dependent variable, the dependent thing that you get from your independent is a real value, and that's y. Make sense? Single variable means one independent variable, and real valued means when you put it through the function, you get a real value out. You get a real value out. Okay, what's a multivariable? Some people are saying z equals f of xy. What do you think? Multivariable referring to? Multiple independent variables. Multiple independent variables taken together give you a single real value, right? So how did these, and what are the graphs of these? Z equals f of xy. Lines. Surfaces, right? Now our independent domain is the xy plane, right? Our independent domain is the xy plane, and for every xy ordered pair, we get a 1z. Put all those z's together, you get surfaces, right? Spheres, paraboloids, planes. Okay? A single variable vector valued function. Okay? Space curve. He says space curve. Is that what that is?
Yeah.
Okay, does that have to be space? Could be 2 dimensions too, right? So these are our, what kind of functions were these? Yeah, so like a parametric equation, or what we said, a vector function, right? Vector function. So like r of t equals? But those ABC are what? Where do we get those ABC? They're functions of the parameter, right? Or or single variable. So here's an example. So what is our single variable? Single variable is the parameter, right? The input parameter. And what do we mean that it's a vector valued function?
It's not a single.
You're going to get a directional.
You put in t and you get out a vector. This is the R2 version, right? And so how will that graph in R2? What will you get for the graph? A curve in xy plane, right? A curve in the xy plane, but it doesn't have to be y as a function of x. It can loop around. It can loop back on itself.
Yeah.
Okay. What have we done? Any other single variable vector valued functions? What's that? Space curve. How would a space curve be different then? What would it be? X of t, y of t, z of t. That's still a single variable vector valued function, right? You still have a single variable t, but now you just get an R3 vector. And how do those graph? Mark said it. Space curve, right? Your vectors, we put all the vectors with their tails at the origin, and all those vectors sweep out a curve in space, right? And that curve might be a line, right? That's this vector. A single variable vector valued function is how we define lines in space. It's just a straight curve, right? And so then we can write some of you said parametric equations, right? So you could write x equals some function of t, y equals some function of t separately, and that's just the parametric form of the same. It's the same thing as that. Okay, so then we come to multivariable vector valued functions. So if we were just keeping this very simple, if we had multivariables meaning two variables that gave us a vector valued function, what might that be? How would you describe that? So like graphically, right? So multivariable, if you have two variables, then your independent is coming from where? We've seen it before, right? We've seen it before. If you have two variables, your independent quantity is what? Right, a point in the xy plane, right? So it's a location, right? So independent is a location. Given that location, x and y together, given a combination of x and y together, what are we going to get from this kind of function? No, what kind? A vector, right? It's a vector valued function. So given a location in the plane, the result of this function will be a particular vector. Given another location in the plane, depending on the function, we'll get a vector. So what we have is a field of vectors. Your location determines what vector you have at that location. That's why it's called a vector field. Does that make sense? So given any point, so this is an R2, so two variable, and then a two vector would be a planar vector field. The independent quantity is a location in the plane. The dependent quantity is a vector associated with that location. No, a two-dimensional vector.
Oh.
You get one vector. You're right. You get one vector, but it's two-dimensional. Right. Mm-hmm. Okay, here we go. So here is an example. So you guys are going to come up with. So what does that look like then? That looks like this. A vector for a location, right? A vector for every location. So then what we'll have is, it's going to be a vector where your x component of the vector could be a function of both x and y, right? So the location, both the x and y coordinates of the location could determine the x component of the vector, and same thing for y. So the y component of the vector is also could be a function of both the coordinates of the location. So here I'm showing you that, so you're going to make a table of values here. When x is -2, so independent, when x is -2 and y is -1, if you're at that location right here, what vector do you get in this particular function? It's unknown. You don't know what the function is, but we're going to try to figure it out. So when x is -2 and y is -1, that's your independent quantity. The vector that you get is what? -1, 2. -1, 2. So when, let's write that out, at -2, comma, -1, the vector we get is -1, comma, 2. So independent quantity is a location in the plane. For every location in the plane, a unique vector. That gives us, so if we were to draw the whole thing, what would we see? So if I was to show you the whole vector field, what would you see on the screen? More than that. It would just be black. The whole thing would just be black, right? Because you have a point everywhere, right? So when you show a vector field, you're not going to show every vector. You're going to just show kind of like a grid of them, right? You're going to show like an array of them spaced apart. But if you showed every single vector, it would just be black, right? The whole thing would be black. Okay, so in this same field, let's just change it up here. So here now, A is 1. So get your independent quantity and your resulting vector. So up here is, if you can't see exactly where that tail is, this is the x and y. And then you're going to figure out what the resulting vector is. Everyone got it? Change it up again. There we go. So get this one. So independent quantity, location. Dependent quantity, the vector associated with that location. Everyone got it? Anyone have a hypothesis for what this vector field is? The general rule, right? I'll do one more. I already did that. Let's do this. There you go. With that. You got all the associated input and output? Okay, what do you think of how can we now write the rule for this vector function? What would be the rule for this vector based on the 4 locations and associated vectors that you wrote down? What do you think the rule is? So what was the second one? -1, +3? +1, -2? Okay, gave us someone who's confident. -2, -1. Next point I gave you was 0, 2. Vector was 2, 0. This last one is -1, 1. Vector is 1, 1. Therefore, sorry, this is a location, not a vector. Sorry. No, I'm not asking for shapes or what the graph looks like. I'm just asking you for the rule, right? So how do we get the vector from the location? So the x coordinate, how does it relate to the x component? How does it relate to the x and y coordinates? It's always y. It's always y. See? And then the y component of the vector, how does it relate to the opposite of x? So this is this vector field, y, -x. You take the y coordinates and you make that the x component of the vector, and then you take the x coordinate of your location and make the opposite of that to be the y component of the vector. So when we put that all together, it looks like this. Okay, so you can kind of think of this, so a common application of vector fields is like velocity field, right? So all these are velocities because velocity has speed and direction. So depending on your location, so it would be like in the water or wind, right? Depending on your location, you have a certain magnitude and speed of water there. Okay? Yeah, right. So, well, that's a very prevalent application of this. So let me just show you some other examples of vector fields here. Here's a wind field around, oh, that one's not great. I like the US one better. Let's see. Let's see. Here's the English Channel. So at different locations, you have different direction and speed of wind. So that's exactly what a vector field is. Given your location, what's your direction and speed of the wind? There we go. So this is also a wind vector field. What's the weather like in Arizona here? Calm, right? Very calm. Vectors are short or 0. So no wind in Arizona right now. How about the Midwest? Right, get your kite, right? Get your kite. You got some pretty strong south and southwest winds. No, wind is where it's coming from, right? So these are